It's my pleasure and my privilege to introduce Dr. Arthur D. Richmond as the 2017 Distinguished CEDAR Lecturer. Art received his PhD in 1970 from the University of California, Los Angeles. His thesis research focused on the ionospheric effects of solar flares and the dynamo, in particular how atmospheric tidal winds due to differential solar heating or lunar gravitational forcing move ionospheric plasma across geomagnetic field lines to generate fields and currents. Prior to his appointment as a scientist at the National Center for Atmospheric Research in 1983, Art held a series of short-term positions funded by the National Research Council, NATO, and NCAR. Art's scientific contributions address a range of topics in geospace physics, most notably the electrodynamics of the ionosphere and the dynamics of the thermosphere. He is a world-renowned leader in modeling of ionospheric electrodynamics and also contributed pioneering research into gravity wave effects on the thermosphere, as well as the thermospheric response to magnetospheric drivers. In recognition of his scholarly contributions, Art received multiple honors, including Fellow of the AGU Nicolay Lecturer, the CEDAR Prize Lecture, and editor's citations for excellence in refereeing from Radio Science and on 2 separate occasions from JGR Space Physics. Art has authored or co-authored more than 200 publications. His papers on the electrodynamics of the ionosphere are essential to modern understanding of how the tightly coupled magnetosphere-ionosphere-thermosphere system works. He established the fundamental physics of the ionospheric dynamo, developed the assimilative technique to map electrodynamic features of the high-latitude ionosphere from localized observations, and led the inaugural effort to include self-consistent electrodynamics into first principle geospace models. My introduction would be remiss if I didn't speak to the notable personal qualities that further distinguish our colleague, Art Richmond. Art the environmentalist has been biking to work for years, long before it was fashionable. Art the mentor has hosted 3 visiting Fulbright scholars from African nations, supervised 18 postdoctoral researchers, and directly shepherded the thesis research of 7 graduate students. Art the mentor has also guided the writing of well over 40 publications with student or postdoc first authors. It is noteworthy that his collective group of protégés includes diverse ethnicities and nationalities, and many women, myself included. Above all, Art the family man is devoted to his beloved wife, Maria, their children, Christoph and Anya, and their grandchildren. As Art embarks upon his imminent retirement, his family will undoubtedly benefit from some added indulgence of his time and attention. I personally hope that Art and Maria will find time for more hikes on their cherished trails in Indian Peaks Wilderness, Rocky Mountain National Park, and beyond. Before Art embarks on his retirement passage, we are fortunate to hear from him today. Please join me in congratulating Art for a remarkable record of scientific achievement and in welcoming him to the stage to deliver the 2017 Distinguished Lecture about his perspectives on ionospheric electrodynamics. Art?
So thank you, Maura, for that introduction, and thanks to the CEDAR Science Steering Committee for the invitation to talk and for all their work in putting together this workshop, which is a tremendous amount of work. So what I'm going to do today is not give a comprehensive overview of electrodynamics, but rather a personal perspective of various projects I've been involved in particular, some interesting things that I've learned over the years. And this has been done in collaboration with many people, some of who will be highlighted in the talk. I'll go fairly briefly over the topics shown here: ionospheric dynamo modeling, the disturbance dynamo, the AMI procedure, interactions of ionospheric and magnetospheric electrodynamics, the Joule heating impacts on the thermosphere, and low latitude evening ionospheric electrodynamics. So I got started in the field as when my thesis advisor, Professor Venkataswaran, suggested that I look at the effects of solar flares on geomagnetic variations and attempt to model these effects. And one of the reasons was we know that the winds in the upper atmosphere are driving the electric currents. So if we can measure the magnetic variations of these currents, maybe it's going to tell us something about what the winds are doing. By the way, Venki was also the professor of this year's CEDAR prize lecturer, Dolores Knipp, and was a mentor to Larry Lyons and many other students, of course. My postdoc mentor, Sadami Matsushita, also worked with me on electrodynamics, and one of his students, Stan Tarpley, we did some modeling. Then when I came to join the regular staff at NCAR, I worked with Ray Roble and Cicely Ridley to develop a dynamo model that could be incorporated with the NCAR TIE-GCM. Again, partly for the purpose of understanding the winds in the upper atmosphere by being able to use geomagnetic variations as diagnostics, but also because the electric fields generated by the dynamo have a significant impact on ionospheric dynamics. So this is an example of a calculated equivalent current pattern. This is some work that we did that Astrid and I did with Vafi Doumbia. And one of the purposes of this study was to look at longitudinal variations of geomagnetic variations, and also to try to assess the relative importance of winds driven by the in situ heating, daily heating of the thermosphere, as compared with the effects of tides propagating up from the lower atmosphere. In this particular study, we could use the model to turn on and off the tides at the lower boundary of the TI-GCM. This is using just migrating tides coming from the global scale wave model. And if we turned off the tides, we found that the amplitude of the calculated effects was reduced. So in this study, the tides were contributing a relatively minor amount, but still significant. Other studies have seemed to indicate a larger importance of the tides. Also, the dynamo gives an electric field, which is associated with plasma drifts in the ionosphere. This is modeling of the vertical drift at the location of Hikamarka throughout the day. And the model seems to produce the general features. There's upward drifts at day, downward at night, with often this enhancement in the early evening, the pre-reversal enhancement that I'll come back to later, that has a strong dependence on solar activity. In this modeling work, I think it was work with Cassandra Fiesen who first showed the ability of the model to produce this pre-reversal enhancement. And more recently, I've been working with Tui Fang and Astrid on this. Some other modeling work has been done with Ingrid Knudsen, who looked at the effects of long-term secular changes in the magnetic field. And more recently, Astrid and I have been working with Patrick Elkin on the effects of gravity and pressure gradient-driven currents in the thermosphere. Well, this is for average conditions, but there's a considerable amount of day-to-day variability. One of the types of variations is the lunar tide, which produces effects on the order of 10% as large as the regular solar variations. And in recent years, it's become apparent that during stratospheric warmings, there are big changes to the ionospheric dynamo. This is an analysis of data carried out by Yamazaki, who was a postdoc working with us, who looked at periods of stratospheric warmings, shown on the top by the zonal mean wind in the stratosphere and the temperature at the pole in the stratosphere, and then extracted the lunar tide, the primary lunar tide, which has a period of around 15 days, using a 29-day running average. And it's apparent that there's a large increase in the apparent lunar tide during these periods of stratospheric warmings. This is just one example. There are many other examples, and it seems that more often than not, you do get this type of effect. So modeling work was done. First, Yamazaki and I did try to model this effect successfully, and we found that it's associated with a strong anti-symmetric tide, semi-diurnal tide. Earlier work on the lunar tides was carried out by Robert Stenning using the global scale wave model, again, which was developed by Jeff Forbes and Maura Hagen. And that study also showed enhancements of the lunar tide during stratospheric warming conditions. More recently, Nick Petitella and Hanli Liu have been using the whole atmosphere community climate model to look at strat warm effects and lunar tidal effects. Another type of variability is associated with the energy inputs at high latitudes from the magnetosphere. And if we, this is a model simulation showing the lower thermospheric winds for quiet conditions at 2 altitudes, 110, 150 kilometers, and for a simulated storm. And we see that there's a very strong change in the winds that extends down to, and this is shown here, down to at least 30 degrees latitude. One of the effects that we see is that at the mid-latitude locations, we tend to develop a westward wind over much of the region. And Hans Foland and Hans Meyer pointed out that these winds might have a dynamo effect in the atmosphere, but they just threw that out as a suggestion. The idea was kind of picked up by Michel Blanc and me, and it was based on observations at mid-latitudes from the Saint-Santin radar, where Michel had done statistical analysis of drifts, ion drifts from the radar, and found that during disturbed periods, there always seemed to be a mean westward drift seen at Saint-Santin, departure from the usual daily variation. And this is not what would be expected by a penetration field that's coming out of high latitudes. It tends to have the two-cell pattern where you would expect reversals in this. So we came up with the idea that, well, maybe this is coming from the winds, and we developed a model to illustrate the effect and called it the ionospheric disturbance dynamo. The model was able to reproduce fairly well the observed observations at mid-latitudes, but it also made a prediction at low latitudes. And we found at, for example, at the magnetic equator, the disturbance dynamo tends to reduce the upward drift at day, that is, produce a negative perturbation during the daytime and an upward drift at night. And Sherlace and Fayer made this comparison between their empirical study of drifts at Hikamarka and found, actually, considering the simplicity of the model that was originally developed, the agreement is, the basic agreement is quite surprising. Other people worked on the disturbance dynamo. One of the main people was a French colleague, Christine Amaury-Mazaudier, and some of her colleagues in Africa and Vietnam who did further modeling of this. Well, at high latitudes, the winds also have dynamo effects. And on the left is again, another modeling study that I did with Ray Roble using the TI-EGCM. So on the upper left is the electric potential that is at high latitudes imposed on the model and the electrodynamics. And shown here are the corresponding winds at 140 kilometers. And you can see some of the pattern in the wind velocity that's associated with the ion drifts in this two-cell pattern of electric potential. With the model, we can do experiments like turn off any field line currents connecting the ionosphere to the magnetosphere, and then recalculate the electric potential, and that's what's shown on the bottom. So these winds are generating this electric potential pattern with no direct connection to the magnetosphere. And we see that we are, again, getting sort of a two-cell pattern. It's weaker than the original, about 1/3 as strong, and a bit rotated in time associated with the Earth's rotation. But the general pattern is that the drifts are generally in the same direction as the originally imposed drifts from the magnetosphere. So the atmosphere is acting a little bit like a flywheel, and Peter Banks pointed this out a long time ago, that the atmosphere tends to have a flywheel effect in maintaining the convection. In order to understand better the winds and just how they're being driven, a student and later a postdoc who worked with me, Youngseo Kwak, got in to do detailed analysis of the forces, vorticity, potential vorticity, and other parameters of the coming out of the model. And this is just one example showing the ion drag accelerations at high latitudes that tend to be associated with this. But there are other forces that are actually larger than the ion drag once we take the full dynamics into account. There's pressure gradient forces, the Coriolis force acting on the wind, the advection, horizontal advection of momentum, which corresponds basically to a centrifugal acceleration. It turns out that these other forces are largely divergent or convergent, and the dynamics of the atmosphere on these fairly slow timescales is such that the pressure tends to adjust fairly rapidly to try to balance out any or cancel out any horizontally divergent flows, so that the final acceleration is not too different from the ion drag. Well, obviously the strength and pattern of the high latitude convection is very important for ionospheric dynamics, and there are many diverse observations related to this convection and to the associated electric currents. So the question came up, how can we put this information together to look at time variations of the high latitude convection and the associated currents? So it started off working in this area, working with Kamide and Matsushita, using ground magnetometer data. This is not an example of that study, but we used ground magnetometer data like that shown here to estimate the currents, the equivalent currents in the ionosphere, and then together with a conductivity model, try to calculate the distribution of ionospheric electric potential. And this seemed to work pretty well. Kamide was primarily interested in looking at the magnetospheric, what these patterns would tell us about what the magnetosphere is doing. I was more interested in terms of what the effects on the upper atmosphere would be. Then we asked the question, well, there's other types of observations. How can we take advantage of those and not use just the magnetometers, but there were, for example, observations of ionospheric drifts from radars and satellites passing across. And so we got into the techniques of data assimilation and developed the AMY procedure to be able to assimilate all these different types of data simultaneously to produce a consistent pattern of electric potential, ionospheric currents, and other effects. Then many other people got in and made great contributions to the further development of AMY. Dolores Knipp was one of the early developers, worked with satellite magnetometer data. Barbara Emery helped a great deal on, often many of these magnetometer data had to be hand digitized, and she helped out with that. Gang Lu, more recently, or actually starting in the 1990s, got involved and has actually taken over most of the lead of AMY-type studies of storms and disturbances. Jeff Crowley and Aaron Ridley worked a lot on developing the data procedures for AMY and the interpretation of the outputs. One thing about data assimilation procedures is they take advantage, they take a Bayesian approach to the estimation problem of the state of the system. and they take advantage of statistical information as well as the actual measurements at any time. So they can use a background models and average models, first guess climatological model, and information about the covariances of the fields. That is, if we have a measurement at one location, what does it tell us about what's going on at some distance away? And the farther away we get, the less information it gives us. So looking at the statistics of the data was also a very important contribution to Amy. At the beginning, we just took guesses as to what these correlation distances were. But then various people have contributed, and one of the important features of Amy is looking at the correlation between conductances in the ionosphere and the ground magnetic variation. An did a lot of studies of this, and we use his results as information to try to improve our conductivity models of the ionosphere when we're using Amy. Other people, like I had a summer student, Abena Pokuawa, who analyzed a lot of IceCat data to look at its statistics. Somebody who was very familiar with the SuperDARN data and statistics was Ellen Cousins, and she came to work with us as a postdoc, and primarily working with Tomoko Matsuo and myself. She developed a technique to come up with improved electric potential patterns from the SuperDARN data, but also taking into account this climatological and statistical information using empirical orthogonal functions to help describe the system. This is an example, in fact, I believe this is still available on the website for SuperDARN, that you can call for the SAM procedure to get electric potentials. We also worked with magnetometer data from the Ampere system, the Iridium satellites, and did a similar type of mapping procedure. And then the difficult part, in theory it should be easy, but combining the Ampere and the SuperDARN data to get joint patterns of the electric potential and the magnetic fields. It turns out that that last step is sensitive to the conductivities that are being assumed or used. And so that's something that needs further development, and Tomoko is working with Dolores and other people on this, and students. Another thing is that so far the Amy procedure does not take into account the high latitude winds, which have some dynamo influence, as I've already shown. So an idea is that maybe we can use something like the TI-EGCM model to help give us information in a time-dependent sense about what the winds are for given electrodynamic conditions. And this is a complicated thing to do, but one step in this direction was carried out by Santiago Marsal and Astrid and me, using the field line currents estimated from the Ampere system, the Iridium satellites, provided to us by Brian Anderson. And we use those field line currents now to drive the electrodynamics in TI-EGCM, and then looked at different outputs coming from this. And one of the outputs of interest to Santi was, could we reproduce ground magnetic variation? So we're starting with observations of satellite of field line currents. The ground magnetic variations, this is at the location of the College Observatory in Alaska. The ground magnetic variations are due more to the auroral electrojets, which are somehow weakly coupled to the field line currents. But we were quite pleased that by adjusting the conductances in the model and the Hall to Pedersen ratio, we could get a fairly good agreement between the observed and simulated magnetic variations. In carrying this out, we found that it's important to have a good model of ionospheric conductivity, and not only in regions where we have large conductivity on the day side and in the auroral zone, but also in regions where the conductivity is small. So the winter polar cap, the night side ionosphere. In fact, this knowledge of these night side conductivities is not very well known. Some of it comes from the lower F region, but there are also significant contributions from the E region. And the sources of nighttime ionization, we have general ideas. We know that there's some EUV radiation from stars, so starlight contributes. There's a contribution from scattered Lyman beta that's scattered from the hydrogen geocorona. Another contribution turns out to be energetic neutral atoms. And I was looking at observations from the Arecibo radar of electron densities over Arecibo, and they were showing a very large increase, order of magnitude increase at night below 200 kilometers during magnetic storms. And I asked Larry, well, what particles are producing this? Where are these electrons coming from? And he said, well, it's not electrons. We have energetic neutral atoms that are coming. These energetic neutral atoms are coming from energetic ring current particles at charge exchange with the geocorona and can be scattered in all directions, including down to low latitudes. If we want to model the effects of energetic neutral precipitation, there's some difficulties that arise. First, if you have an energetic neutral coming into the atmosphere, it does tend to charge exchange. It will get ionized and become charged, and then all of a sudden it feels the magnetic field and starts gyrating. But then it will have another collision and grab another electron back from an atom and become neutral and then head off in a straight direction. In work with Marina Galland, who is interested in the proton aurora, and as far as this cycle of neutral versus charged states of the energetic particles, this proceeds several times to alternate between neutral and charged states. We realize that the magnetic field, that these neutral particles are effectively can be mirrored away from the Earth in a manner very similar to what we have for charged particles coming in. And this is an example of an oversimplified example, but of a neutral coming in, getting very briefly ionized, in which case its motion perpendicular to the magnetic field is randomized, and then it becomes neutralized and heads off in some direction. It keeps its parallel motion, but its perpendicular motion is randomized. So it's a little bit, in this case, a two-dimensional case, it looks like it's reflected off of the magnetic field line. We continue through this procedure, and we find if we have magnetic field lines that are converging toward the Earth, after multiple times, this neutral particle will start heading out again, just as if it were a charged particle being mirrored. And so we were wondering, well, okay, what is the relative importance? How does this mirroring effect compare with charged particle mirroring? And it turns out that it's identical. That is, if you want to look at the effects of mirroring on precipitating protons, you don't have to worry about whether this energetic particle is neutral or charged, because the rate of change of its pitch angle with time as it comes into the field is identical whether it is neutral or charged. So I'll move to the topic now of coupled magnetosphere-ionosphere-atmosphere modeling. I've worked with a couple of groups on this. In this case, we're looking at the effects of hot plasma in the inner magnetosphere. We're not dealing here with MHD models of the magnetosphere, which are important for farther reaches of the magnetosphere. But the hot plasma in the inner magnetosphere has a tendency to react with the electric fields that it experiences. They couple it with the ionosphere, and to react in such a way that in a steady state, any electric field imposed at high latitudes tends to be largely shielded from lower latitudes. This is called the steady state shielding effect. But if it's not a steady state, we have situations of undershielding or overshielding. And in order to try to simulate these effects, the first person I worked with on this was Christoph Peymerat, who came as a postdoc, and coupled his model of intermagnetospheric convection with the TI-EGCM, and we ran simulations and looked at the importance of these shielding, overshielding effects. One study we did with us and Kobeya on the penetration of electric fields to the equator. And then more recently, Naomi Maruyama has been leading a group of coupling the CTIP-E model with the Rice convection model, which is another model of the intermagnetospheric convection, and carrying out simulation. So this is work done. Tim Fullerell is a developer of the CTIP-E model. Stan was the main person working with the RCM, Rice convection model. And the results for a realistic storm are, of course, complicated. But having a model like this allows us to look at the relative importance of different effects. For example, the relative importance of the disturbance dynamo winds versus the direct penetration of electric fields from high latitudes to low latitudes. We can do this by turning off either the high latitude potential and keep the winds going, the disturbance winds, which produces disturbance dynamo, or turn off the winds and just look at the penetration of electric fields from high to low latitudes. And during the daytime, which is mainly the right half of this diagram, we find that the two effects are fairly additive. That is, if we look at the disturbances, the departures from the average quiet state due to the disturbance dynamo and the direct penetration, they add. But at night, the situation is different. They no longer add. And it takes a little while to look at these curves at the night. But Naomi found that at night, the electric fields are changing the conductivity, which comes largely from the F region at night. So if you raise or lower the F region, it changes the conductivity. It also changes the winds at night, and that changes the whole system. So now we can't just ask the question, is this disturbance dynamo or direct penetration, but we have an interactive system between them. If we want to try to simulate realistic conditions and compare with observations, early models use a dipole field to represent the geomagnetic field, but it turns out that the non-dipole distortions of the field have a significant influence, will often have a significant influence on the electrodynamics. And let me start first on the right side of this diagram. This is using magnetic apex coordinates, which are based on a realistic geomagnetic field, the IGRF. John Emmert helped develop some of the software for using this model, and Carl Laundau also helped contribute to the development of the theory of it. So we use the apex coordinate routines to look at a particular question. What if we have a location, say Arecibo radar or Millstone Hill radar, and we trace along the magnetic field back to its conjugate point in the southern hemisphere, and let's just suppose that we have a purely horizontal eastward, magnetic eastward drift of 100 meters per second at the conjugate point, and assuming equipotential field lines, what is that drift at Millstone Hill? Well, it is eastward, but it's weaker because the magnetic field is stronger in the northern hemisphere. But also now, because of the field distortions, we have a significant meridional component of drift, even though at the conjugate point there's no meridional drift. The same thing at Arecibo. And this is significant because the meridional drift has a vertical component that does have a significant influence on the ionosphere. The upward and downward motions due to this. Well, another effect, I worked with another summer student, Sarah Gasta, to analyze at auroral latitudes what what is the influence of the non-dipole part of the magnetic field to various factors. And one thing is that if we take a magnetic latitude of 68 degrees and go around, well, in the southern hemisphere, we're going to run into the South Atlantic anomaly where there's a weak magnetic field. The conductivities of the ionosphere are inversely dependent on the magnetic field. So we have larger conductivities in the South Atlantic than over by Australia. Another effect, though, is that if we have an electric potential pattern, say a Weimer pattern, that's organized with respect to magnetic latitude and magnetic local time, and let's just say that we fix that on the Earth and then rotate the Earth under it. As we map that pattern to geographic coordinates, that pattern in geographic coordinates is going to be distorted by this mapping. And these distortions correspond to changes in the gradient of the potential and therefore changes in the electric field as we go around in longitude. So we looked at the case of if we have a north-south electric field and combine that with the changes of conductivity, what does that do to the Joule heating with respect to longitude? And in the southern hemisphere, we find a maximum in the South Atlantic anomaly. In the northern hemisphere, there's a more interesting feature. We get two peaks of heating, roughly over Alaska and Iceland, with minima around Hudson Bay and Siberia. And this is due to those distortions, the strengthening and weakening of the electric field. And there's about a factor of 1.8 difference here. So it's not a negligible effect. Okay, if we're looking at Joule heating, we want to know the horizontal variations of it, but probably even more importantly, what are the vertical variations of the heating? And how does this impact the thermosphere? This is based on a study done by Yanxi Wang, who at the time was a student of Yue Deng. And on the left, we're showing here some modeling work using the TI-GCM and looking, just to simplify things to one dimension, to take a first look at it, we're doing global averages in the horizontal. So we're running the three-dimensional TI-GCM, but then looking at global averages. And the global average heat, Joule heating per scale height is shown by these black lines for solar maximum, the solid line, and solar minimum, the dashed line. And the vertical scale is in log pressure. So one scale height actually corresponds to the width of either this red or this blue slab shown here is one scale height thick. And not surprisingly, at solar maximum, there's more Joule heating because we're using the same electric field, but the conductivities are larger at solar maximum, 30–40% in the E region, but more than a factor of 3 when we're up in the F region. So there's a very large variation in the F region conductivities. Now we can ask the question, okay, what if we just say turn off the heating in one particular slab, like this red slab shown here, and then look at the consequences on the density, the global average density at 400 kilometers. And we can do this at each scale height in order to see the importance of heating that's going in at that particular height. Well, the first thing we find is that the altitude that has the greatest impact on density at solar minimum is not where most of the heating is coming in down here, but actually somewhat higher, scale height higher up. At solar maximum, the altitude of maximum impact is not even in the E region at all, it's up in the F region. It's this blue region that's having the maximum impact on density changes. And if we look at a time, that would be for steady state, but if we look at a time varying situation, as shown on the right here, where the time is in days, for short times, less than 12 hours or so, the impact on the high altitude density is always coming from the F region. And even though most of the heat is going into the E region. So we have to be careful about just using measures of height integrated Joule heating to explain density variations. The distribution of heating and the fraction of heating going into the F region is very important and can be quite variable. Well, just one more interesting highlight. We're looking at the effects of Joule heating, and a student of Jinxiao Chu, Wei-Chun Fang, analyzed the LIDAR data, temperature data at McMurdo in Antarctica, and found that once we got above 100 kilometers, up to 110, the limit of the observations, there was a very rapid increase in the diurnal variation of temperature seen there. And so they went and worked with Tim to use the CTIP-E model and was able to reproduce this rapid increase. But there's a curious feature here because according to the model, the temperature increase peaks and then drops off again before starting to increase again. So is this a Joule heating effect? We're in Antarctica. It turns out, no, it's not really a Joule heating effect that's causing this diurnal temperature variation. When Wei-Chun did a simulation with the model where he turned off the Hall currents in the model, the Hall drag, and if those Hall drag is turned off, the amplitude of the low altitude temperature variation gets much smaller. So the dot dash curve is for only Joule heating. So what's happening is that the Hall currents in the lower atmosphere effectively correspond to ions trying to move in the direction of the electric field, which is at these low altitudes either going to be divergent or convergent, depending on if there's a high or low potential. And McMurdo tends to be roughly in the center of one of the cells of the two-cell pattern. So if we're at a time where we're pushing the air together, these ions are colliding with neutrals, they're pushing the air, it induces a downward motion and an adiabatic temperature increase. For divergent forcing, we get an upward motion and a decrease in the temperature. Okay, the final subject is low-latitude electrodynamics. And this is work I did with Tsu-Wei and Astrid and another summer student, Will Ivanovsky, who is at the meeting. I don't know if he's in the room. Looking at how can we explain this pre-reversal enhancement? What causes this curious feature? And in order to do it, again, we did modeling. We used the TI-EGCM, but because of questions about what the upper boundary conditions of the TI-EGCM at about 700 kilometers, what influence that might have on the equatorial region, we coupled it with a global ionosphere-plasmasphere model that's a flux tube model and goes well out into the plasmasphere. This shows 3 different parameters in the evening at 19 local time for the longitude of approximately of Hikamarka. So we have we're going in latitude here, geographic latitude. The magnetic equator at this longitude is about 12 degrees south. The white dotted lines are magnetic field lines. And we have an aspect ratio of about 1 here, so height and horizontal distance are roughly equal in this projection. We see the equatorial ionization anomaly, the 2 maxima of electron density either side of the equator. The F region is quite high at this time because of the preceding upward drifts. The Petersen conductivity depends on the electron density, but also on the neutral density. It's basically the product of the 2. So it maximizes at the bottom edge of the EIA, the F region, on both sides. And at the equator at this time, it's very small. In fact, it's an order of magnitude smaller in this case. The zonal wind is the main thing driving electrodynamics at this time. And red is eastward, blue is westward. So at this time, there's a fairly strong wind shear going from westward at low altitude to eastward higher up. This eastward wind, it turns out, is accelerating in time because a few hours earlier at this time the wind was westward, but after sunset the wind is accelerating to the east. Okay, one important thing in looking at the electrodynamics, and this was pointed out actually by Dave Anderson and Mike Mandillo many years ago, is that the electric field perpendicular in the meridional plane, or vertical if we're at the equator, that electric field and its associated E cross B velocity, the plasma velocity tends to correspond to the average wind along a particular field line weighted by the Pedersen conductivity. So if we're at one of these low altitude field lines, most of the Pedersen conductivity, perhaps you can even see here, there's a very weak E layer of conductivity. Most of the conductivity is coming from the E region. It's only when we get to these higher altitude field lines that we're getting contributions to this plasma drift coming from the F region. But we can then expect on field lines that are out here in the EIA that the plasma drift is going to be eastward at roughly the neutral wind velocity here. If we look at the vertical drift, the situation is different. We can't just look at individual lines, field lines, to look at estimate the plasma drifts. We have to consider the whole system. And if we're looking at Hikamarka, say at 300 or 400 kilometers, it turns out the vertical drift is not being produced locally. It's not even being produced along the same field line. It's being generated by what's happening out here in the EIA region. So this is a sketch of what is going on. The orange slabs are those regions of Pedersen, F region Pedersen conductivity. The blue arrows show the neutral wind that is accelerating with time. It's small around sunset. We're looking at a 2-hour local time period in the ionosphere. So the neutral wind is accelerating. It's tending to drag the plasma with it and produce an E cross B drift similar to it due to the effect that I just discussed. But now we have a problem because the electric field has to be curl-free. This is something pointed out by Vince Eccles. In fact, he's the one who sort of came up with this basic explanation for the pre-reversal enhancement, following up on ideas of Henry Rishbeth. The fact that the electric field is curl-free means that the convection, the E cross B convection of magnetic flux tubes, in this case, is diverging in the east-west direction, but we can't change the magnetic field strength. So if we have a divergence of the velocity in the east-west direction, there has to be a convergence in the meridional and vertical direction to offset this so that there's no net generation of magnetic field. And in order to get that convergence, the easiest way for the ionosphere to do it is by pulling up flux tubes from lower altitude. So we want to get convergence around here. We do it by pulling up magnetic field and producing E cross B velocities at lower altitudes. And this is basically the pre-reversal enhancement. Okay, there's there's a few complications to this, and this is already simplified. One is that if we're down at 100 kilometers, there is some nighttime ionization there. There is a weak equatorial electrojet going on. And we have an eastward electric field here, corresponding to the upward velocity, an eastward electrojet current. The E.J is positive. It means we're dissipating energy. That energy is coming out of the system that's driving this plasma convection. So, in fact, if we increase the E region conductivity, we'll reduce the upward drift, but also it turns out we reduce the horizontal drift at the upper altitudes because the whole system is connected. A further complication, if we reduce the horizontal ion drift, the difference in velocity between the neutrals and the ions would increase, and this would increase ion drag, which is going to slow down the neutrals. And it turns out Henry Rishbeth pointed out that we tend to get sort of a fixed amount of ion drag on the air that balances the day-to-night pressure gradient that's driving the neutral winds. So the equatorial electrojet at night, the E-region conductivity, is affecting the wind velocity in the F region. Okay, just to make a few concluding remarks, I think I pointed out that ionospheric electrodynamics involves many types of interactions, ionization, the dynamics of the ionosphere, neutral dynamics, coupling with lower atmosphere, coupling with the magnetosphere. And it's such a broad topic that it really requires good collaborative research to make progress. And I pointed out actually just a few, or just some of the collaborators, my own collaborators on this topic. There have been many more, many of my colleagues at HIO I've left off, many other students and postdocs I've worked with. If we're looking to the future, we always want to have more observations, and particularly for something like AMY, we don't want to have big data gaps. In order to study lower atmosphere coupling, whole atmosphere model is essential. Coupling with magnetospheric models is also very important. And in order to tie all of this together, the observations and the models, we can really take the best of each and get the power out of the whole system is developing data assimilation techniques. Thank you.
So this is the 2017 CEDAR Distinguished Lecture Award presented to Dr. Arthur D. Richmond from NCAR in recognition for outstanding scientific contribution to the coupling, energetics, and dynamics of atmospheric regions, the CEDAR community.